Hello and welcome. This is going to be our lecture video for December 3rd. Goal for today is to be able to find the zeros of a polynomial using synthetic division. Why synthetic division? Well, synthetic division is a fast way to evaluate a function, but you get this added bonus that if you find a zero, the bottom row of the synthetic division is going to give you the new coefficients for a simplified or kind of shrunken polynomial. It will take a cubic down to a quadratic. It'll take a quartic down to a cubic, and so on. It will always reduce the degree of your polynomial by 1. Okay, so when you're finding zeros, it's good to know when you found all of them, and that requires something called the fundamental theorem of algebra. Let's add this into our notes. Fundamental theorem of algebra states that you get as many roots / zeros as the biggest exponent. Example, a quartic has 4 roots. Hopefully remember that vocab word quartic. That's a polynomial where the biggest exponent is a 4, and therefore it should have 4 roots. But to get these 4 roots, you might have to count a little bit funny. You've got to count your multiplicities separately. So a double zero counts as 2 separate zeros. And you also might have to count some imaginary zeros. But if you allow for that, then this rule is always true. You always get as many zeros as your biggest exponent. All right, rational root theorem, another one for our notes. If a polynomial has any rational roots, they will be factors of the constant. So every polynomial has a constant at the end. If there's not one, then it's implied to be 0. But in that case, we can't apply this theorem. You have to have a number there for your constant. So if a polynomial has any rational roots, they will be factors of the constant. There's a slight caveat here that so we would write it, it's last over first. This only applies if there is a leading coefficient. For the most part, I don't worry too much about this because generally once we find one answer, it shrinks our polynomial and then we can use a new technique. But technically, to write out all of your possible rational roots, you have to do factors of the last constant term divided by factors of the leading coefficient. Now, 1 will always be a factor of that leading coefficient, so that's why we can just focus on factors of the constant. Technically, to get them all, you have to do last over first with every combination of factors of the last term divided by factors of the first term. Okay, factor theorem. This one's really easy. If x minus a is a factor, then a is a root. This comes to us directly from the zero product property. you set your factors individually equal to 0 and solve, but factor theorem allows us to just go straight to the answer one step quicker. Okay, so how do you do synthetic division? So here's my polynomial. So y equals, then we got this cubic function, and I want to evaluate it at x equals 3. So one thing I could do is just plug in a 3 for every instance of the x and then solve. That it's going to take a little bit longer. There's a shortcut here where you just write down the coefficients from your polynomial. So we don't see a number here, so it has to be a 1. So 1, 2, negative 21, 18. So just the coefficients. You put them into a grid like this. You put the 3 over here, and then the pattern is add the column, multiply by your value over here. So 1 plus nothing is a 1. 1 times 3 is a 3. Add the column, we get a 5. Multiply by the 3, we get a 15. Add the column, we get a negative 6. Multiply by the 3 again, we get a negative 18. Add the column, and we get a 0. So this is the y value at x equals 3. Because it's a 0, this is a very special point. This is also an x-intercept. So 3 is an x-intercept. And often when we do the synthetic division, we're trying to get a 0 there because we're trying to find the x-intercepts. And that's how you do synthetic division. Write out the coefficients, and then it's this zigzag pattern of add, multiply, add, multiply, add, multiply, add. All right. Now let's use synthetic division to solve something like this, and let's combine in a little bit of rational root theorem. So let's write out all of our possible solutions. So possible solutions. Rational root theorem said they've got to be factors of the last term. So what numbers divide into 15 evenly? Well, 1 divides in evenly, 3 divides in evenly, 5 divides in evenly, and 15 divides in evenly. But these are integers, so we have to include their negative versions as well. Negative 1, negative 3, negative 5, and negative 15. And now that last over first thing comes into play because technically I have to now take all of these and put them over 2 because I do have a leading coefficient that's not 1. 2 has got the factors of 1 and 2. So take all of these and put them over 2. But really, I'm just doing this for posterity, really, because I'm really hoping that I have a solution over in this side with just the integers. Because once I find 1, then you can use a different technique to find the rest. But okay, so 3 over 2, 5 over 2, 15 over 2, negative 1 over 2, negative 3 over 2, negative 5 over 2, negative 15 over 2. So if this function has any rational roots, it is somewhere in this list. But we're going to start with the small numbers. We'll start with a positive 1 and see if we get it. So I'm going to evaluate at 1 using synthetic division. Let's see what happens. So I drop down the 2. 2 times 1 is 2. Add the column. Negative 3. Multiply. We get a negative 3 here. Add the column. Negative 31. And this is not going to be a 0. So let's just cross out the 1. All right, try it again. We'll try it with negative 1. So 2, negative 5, negative 28. 15 are my coefficients. Now I'm trying it with negative 1. All right, add the column. 2, multiply, negative 2, add, negative 7, multiply, positive 7, add, negative 21, multiply, we get 21. This one's not going to end up being a 0 either. Okay? Try it again. 2, negative 5, negative 28, 15. This time I'm trying 3. So drop the 2, 2, 6, 1, 3, negative 25, negative 75. This one's not going to work. We'll try negative 3. Two, negative 5, negative 28, 15. Try negative 3, so drop the 2, negative 6, negative 11, positive 33, positive 5, negative 15, and at last we do get a 0. So negative 3 is a root. We'll come back up to our list, circle it, put a little check mark next to it. So we found one. We don't have to now keep checking the rest of them, because at the same time as finding this one, we shrunk our cubic down to a quadratic. These numbers here at the bottom of synthetic division become the new coefficients for a new quadratic. 2x squared minus 11x plus 5 equals 0. Now we've got lots of ways to solve quadratics. I'm going to use the quadratic formula here. So negative b plus or minus the square root of b squared minus 4ac, so let's see, that's 8 times 5 is a 40, all over 2a, so we have a 4. Now 11 plus or minus the square root of 81 all over 4. 81 is a perfect square, so this becomes 11 plus or minus 9 all over 4. Now is a good time to split it into the positive and the negative case. So 11 plus 9 over 4 and 11 minus 9 over 4. 11 plus 9 is 20 over 4, which becomes a 5. And this one over here becomes 2 over 4, which we simplify to be 1/2. Let's go, these are both rational, so let's go see if they're in our list. Yep, 5 was on our list, and 1/2 was in our list. So a little double check there if you do get rational solutions. So once again, all of our answers are x equals, you might see it with a set bracket, and in numerical order, -3, 1/2, and 5. Fundamental theorem of algebra says we're expecting 3 roots. We got all 3. All right, one more. Promise this one to go a little bit quicker. Let's write out our search area. So possible roots for 5 are just 1 and 5, or -1 and -5. There is this leading coefficient, so we have to also include 1 over 2, 5 over 2, -1 over 2, -5 over 2. All right. And let's check 1 and -1 first. So 2, -3, 6, -5. We are checking 1 first. So drop down the 2, multiply, add, multiply, add, multiply, and look at that, we got it on our first try, the value of 1. All right, take these coefficients and turn them into a quadratic. 2x squared minus x plus 5. Again, this is still equal to 0. And I'm going to go straight to the quadratic formula again. So -b plus or minus the square root of b squared minus 4ac. So 4 times 2 is 8, times 5 is 40, all over 2a. Simplify this down, and we get 1 plus or minus the square root of -39 all over 4. We never want to leave a negative inside of a square root, so we're going to pop out that negative as our imaginary unit I. x equals 1 plus or minus the square root of 39i all over 4. All right, and then we also have the answer of 1, which is the one that we found using synthetic division. We were expecting 3 answers because this is cubic. Did we get 3 answers? We did, because this plus or minus makes this count as 2 separate answers. 1 plus root 39i over 4, 1 minus root 39i over 4. Okay, I'll embed one more for you to solve on your own. I promise it will have all rational roots. You just got to tell me what they all are. And we'll call that good for this video. Have a good rest of your day.